Hi folks, so in this video we are going to talk about polynomial functions that have repeated roots, and it'll make sense once we actually see our example here. So I'm going to draw what looks like a cubic polynomial. So I'm going to say f of x, oopsies. I'm not going to give a particular equation here because we're going to build the equation, but here's the graph. F of x is going to look like this. So let's pretend it's got a root right there, and then it's already kind of messed up, not what I wanted to do. It looks like this, and then just touches that second one right there. Okay. So let's suppose that this root is at, I don't know, say 3, and this one back here would be at -2. I'll ignore the scale. Alrighty. Okay. So my question is, what is the equation of this function? So based on the shape, it looks like it has to be a cubic function. So we know that if we assume it's fully factorable, it's going to be f of x is equal to x minus something, x minus something, x minus something. At most, it'll be 3 linear factors. Okay, since we know 2 of the roots, then we already know what at least 2 of the linear factors are going to be. Since we have x-intercept at -2, we can plug in just x minus -2 or x plus 2, and another one at x equals 3. Okay, so again, this root comes from the x equals -2, x equals +3, and these are the roots. And again, we talked about when we were talking about rational functions and just factoring in general, how the roots kind of are connected to the factors of the function, the linear factors, that is. But here's the thing that's a little weird, is that we have a third one, right? And so we know it has to have another linear factor because it already has 2 roots, and it's odd. So here's what I mean by that, is that there has to be 3 linear factors at most. And if these 2 are indeed actually roots, then these factors are kind of non-negotiable. They have to be there. So the question is, what does this third one have to be? Well, the only thing that could possibly be the answer here is another factor of these, either x minus -2 or x plus 2 or x minus 3. So which one is it? Is this factor x plus 2 or x minus 3? Well, let's take a look at it. And let's just try both of them and just see what happens. So let's pretend that this is the answer. So let's pretend this function actually is x plus 2 squared times x minus 3. Ready? And what we're going to do is kind of create a quote-unquote sign chart. And so what this does is this tells you at a certain x value, is the function positive or negative? Let me move my mouse out of the way, sorry about that. Okay, so at 3. So we know so we'll say here's the y value, or the output, f of x, and here's x. So when x is equal to -2, we know it's 0. When x is equal to positive 3, it's 0. Okay, so what's happening between there? Well, when x is less than -2, what does this look like? Well, okay, so for example, x equals -5, then we know the function is, let's see, the x plus 2 part is negative, but since you're squaring it, it turns out positive. And then when I multiply that by x minus 3, well, that part is going to be also negative. So this part right here will actually end up being negative. Alrighty, actually I should write that above here because we're talking about the y values. This is going to be negative. Okay, what happens when x is way bigger than positive 3? So we're talking about over here. Okay, well, when this number is positive, now first off, note that no matter what x is, this part is always positive because it's being squared. If it's not 0, we already know when it's 0, and that's when x is equal to -2. So if it's not -2, this part has to be positive, and so positive number times this would be positive in this area over here for x is greater than 3. And so we have positive times positive, which is a positive number. And again, that's going to fit. So let me just actually reiterate that. So this part squared is always positive times negative. This part over here is going to say positive times positive. And let's see what's happening in the middle here. Well, in the middle, again, we have another positive part, so that can't possibly be any different. Oops, positive. And then, well, when x is between these numbers, and so x is less than 3, this is actually going to be negative here. And so this actually ends up being negative. And check this out. In our function is negative. Oops, sorry, not positive. Negative, positive in the middle, and then positive again. So our graph, this function right here, would not actually work. So it must be the other one, but let's just double check. Okay, let's plug in f of x, and let's call that x plus 2, x minus 3. And let's scooch over here, squared. We'll create another sign chart here. So we'll have, again, our x-intercepts are the same. So now this part is always positive. And let me separate this off. The second piece is always going to be positive. Again, our x values are on the bottom, our outputs are actually on top. Actually, technically this should be on top as well. So imagine all of these are up here. Sorry about that. Okay, so let's clean this up. Okay, sorry about that. Okay, so again, this part's going to be positive, the second piece. And let's see, when x is very negative, then a big negative number plus 2 is still negative. And so we're going to end up with a negative times a positive, which is equal to negative. Again, at -2 we have 0, and at 3 we have 0. We'll go all the way to this end. This would end up being a positive number times another positive, so that's of course positive. So that checks out, just like that one. And in the middle here, well, again, the x minus 3 term, when it's squared, will always be positive. And when x is greater than -2, then this term is positive. And so we have positive times positive, and therefore the outputs should also be positive, which is exactly what they should be. Sorry about that. Right here. Okay. I want to point something out here. Notice that when we looked, we're going to look at the sign charts here, so let me clean this up. Notice that when I had an even power on this factor, this linear factor, when there was an even power, what happened? We went from negative to negative. And if I was to sketch this function, the graph would actually look something like this. We would start off negative, so here's -2, -2, and at +3, we would start off negative, we'd hit it, and we kind of, I like to say it bounces off, so it kind of bounces back down, and then eventually it comes back up to hit that x-intercept at 3, and then becomes positive. Whereas this one, and we already drew this one, but we'll double check. Again, -2, 3, it starts off at 2, and then it goes from negative to positive, and then comes back down, and then at x equals 3, it's coming down positive, and then continues being positive by bouncing off. Okay? Notice, this is a result of the even power here. Okay? So that even power is what causes the graph to kind of like bounce off, and if you kind of look at it, what does it look like around that area right here? If you kind of block off everything else, the graph kind of looks parabolic in shape. Again, it's not exactly a parabola because there's other stuff going on, but it looks like a parabola. It looks like a U shape, or a downward parabola if we were going from negative to negative. Okay, this is directly a result of the, that even power. And likewise, we can see here that when we had an odd power on the factor, the graph just went straight through. It went from negative to positive, or, well, I guess negative to positive still here as well. Okay, this has a direct effect on the graph, so let's break down some vocabulary. Okay, so the multiplicity, fancy word, but it really doesn't have too crazy a meaning, of a root is the number of times it occurs, and that sounds a little weird, is the number of times it occurs. Okay, and so what this means, well, let's take a look at this. So in our function right here, let's just take a look at this. F of x is equal to x plus 2, x minus 3 squared. But instead of writing it squared, I'm going to write it out like this, x minus 3. So let's pretend we didn't know what exponents were. We just had to write them all out. All the factors, we write them out. And so we could say that the roots would be this. X equals -2, 3, and 3. Okay? So since the number 3 comes up multiple times, twice, it has a multiplicity of 2. So we would say the root at x equals -2 has multiplicity 1, and at the root x equals 3 has multiplicity 2 because it occurs twice. Okay. Now, if we draw the connection to the graph, we can see here that the multiplicity of all the roots is actually equal to the degree of the polynomial. Notice, these are both third degree polynomials. So let me actually highlight them because we have a lot going on here, sorry. These are third degree polynomials, so they should have 3 roots. But notice that they don't, they only have 2. So we're gonna kind of fine tune what we said before actually, where we said an nth degree polynomial, an nth degree polynomial has, whoopsie, let's write it out a little bit better. So let me get, this is going to take a long time, so let me come back to you. Okay, so I wrote it out a little bit nicer, and this is actually the fundamental theorem of algebra. It has such a cool name that I wrote it in rainbow. So what does it actually say? In essence, it means that an nth degree polynomial has n roots. And now we said, like, wait a minute, I thought so that says it has n. It doesn't have at most n. And you would think, well, hang on a minute. We said before that we have an example here of a third degree with only 2 roots. You're correct, but the way that this is kind of counting them is it's counting every single one separately, even if it's repeated. So for example, if something has, like above, we have the roots, you know, at x equals 2, 3, and 3, it counts each of them individually. So it would have 3 roots. Okay? Another way to say that, which is again the same thing, is that if you add up the multiplicities of all the roots, so this would be again multiplicity 1, this would be multiplicity 2, that equals the actual degree of the polynomial, which is n. Like our example, we had a third degree and there was 2 roots, multiplicity 1 and multiplicity 2. Okay, so these are the same thing. Now you might be scratching your head about one thing, and I'm going to discuss that in the next video. Alrighty, so hang on to that question if you're thinking of the question I'm thinking of, and I'll see you in the next one, folks.